Good morning, everyone. First, I want to thank the organizer of this symposium for inviting me today. My talk is in a collaboration with my thesis advisor, Oscar Mesa, and as you may see, it has a very suggestive name. It's called Condensation-Induced Atmospheric Dynamics, a New Theory of the Region of the Winds. Very interesting question. This work is highly theoretical. So I worked very hard in this presentation to try to summarize in just 20 minutes the key idea of this work in a scientific divulgation way. First, I want to thank that this work has been possible thanks to partial funding from fellowships from the Universidad Nacional and Sapienza and Las Amundos. And what I want to answer today in this talk are basically two questions. First, you may wonder, what is condensation-induced atmospheric dynamics? That is also known as the biotic palm hypothesis. And the second question that I want to address here is this new theory a new theory of the region of the winds? So let's first go very briefly of what we understand today of the region of the winds. First, a very simple way to look at how the region of the wind is to think of the differential heating of the Earth by the sun and the pressure gradients that this differential heating creates, moving the air and creating what we know as the winds. That's roughly how we understand the atmospheric dynamics today. Of course, this picture and the real picture is more complicated than what I have said. But I guess that the main idea to understand what I'm going to say today is clear. Now, we're ready to talk about what is condensation-induced atmospheric dynamics. But let me give you a small background. Two Russian scientists, Anastasia Makareva and Viktor Gorshkov, that hereafter I'm going to call them the Russians for simplicity, have been working on a new controversial theory that was first published, I might be wrong, but in an English peer-reviewed paper in 2007. They have some previous works in Russian, but this was clearly the first step for their proposal into their international community. The paper is called Biotic Pump of Atmospheric Moisture as Driver of the Hydrological Cycle on Land. And in this paper, they studied how precipitation changes as you move inland from the coast. What they found is that the precipitation over extensive natural forests, these green lines in this picture, does not depend on the distance from the ocean along thousands of kilometers. From this result, they inferred that there is some physical mechanism that transports atmospheric moisture inland from the coast, mechanism that they call the biotic pump hypothesis. And it's called that way because it provides a physical mechanism for the big forests to import moisture from the ocean inland, the continent. I will not discuss the biological implications of this hypothesis, but I will focus only on the key physical core. And the key physical core of this hypothesis is behind the well-known definition of hydrostatic balance. In hydrostatic balance, we all know that the vertical change of the total pressure is balanced by the weight of the gas. But atmosphere and atmospheric air is a mixture of different gases like oxygen and nitrogen, and the Russians defined what they call aerostatic balance. Aerostatic balance is just like the hydrostatic balance, but just for each component of the gas. So for example, If I say that nitrogen is in hydrostatic balance, I can say that the weight of the whole nitrogen is balanced by the vertical partial pressure gradient of the nitrogen alone. And the same applies for the other gases that compose the air. It's clear that if we have a completely static air, I mean no motion at all, we will have aerostatic balance and we will have hydrostatic balance. But real atmosphere complicates a little this picture. So let's focus on the troposphere, the lowest layer of the Earth's atmosphere and where most of the weather happens. And this layer has very interesting properties. For large-scale motions, the Earth's atmosphere is to high degree occurrency in hydrostatic equilibrium. This layer is well mixed, and this means that the concentration of the gases, at least in the dry part of the air, are relatively constant throughout this layer. And what is really important, the pressure and densities of these gases decrease with altitude at the same rate. The consequence is that in the real atmosphere, for a large-scale motion, we will have hydrostatic balance, but the components are not in hydrostatic balance. Fortunately, the dry air components are just slightly away from hydrostatic balance, and the difference cancel each other, so we don't have any problem with them. The complication comes when the next player in this game comes to this picture, the water vapor. Water vapor is a particular gas in our atmosphere, and it has the interesting property that water vapor can easily condense under typical atmospheric conditions. This brings to us the well-known classical Clausius-Clapeyron equation that tells us that during condensation, water vapor changes pressure, but it's not a it doesn't change as it wants. It's restricted by this equation. So when we have hydrostatic balance with water vapor, and water vapor wants to be in aerostatic balance, condensation forces the water vapor to be out of aerostatic balance. And this violation of aerostatic balance is manifested as a strong compression of the vertical distribution of water vapor. This leads to the Russians to propose the appearance of an uncompensated vertical force that they call the evaporative force, and it has this is like the proposal they show, where the force is proportional to the vertical gradient of gamma, and gamma is something like the specific humidity. Using this force that supposedly doesn't appear in the classical theory, they propose a new view of atmospheric dynamics. This evaporative force creates horizontal fluxes of moist air from the area with weaker evaporation to the area where the evaporation is more intensive, and this explains all the main atmospheric circulation. The Russians tried to explain all these physical coordinates hypotheses in a paper published in 2013, and this paper is very singular. First, it was published despite it was rejected by the referees, and the editor added at the end a very large comment, and I want to highlight some sentences from this comment. This is not very usual in peer-reviewed journals. One thing I want to focus is the editor published the paper despite the reviewers rejected it to promote the scientific dialogue. The paper is highly controversial and seems to be in contradiction to common textbook knowledge, and I want to emphasize common textbook knowledge is going to be important later in this presentation. And the editor is not convinced that this view is wrong. So this brings us two big questions that motivated this work. First, if it's true, why hasn't anyone seen this force before? And if it's false, why hasn't anyone shown that this is wrong? So we've been working very hard to answer these questions, and I'm going to give you what are the answers that we found right now. In the rest of this talk, I'm going to show you one key idea that allows us to say what I'm going to say. Our answers are, what hasn't anyone shown that is wrong? Is because it's not wrong, at least the main physical core. Why hasn't anyone seen this force before? Because this force is in fact implicit inside the classical picture. So this force has always been there. The key word is common textbook knowledge. And we decided to go to all the most classical textbooks in atmospheric thermodynamics, the ones in these pictures and other more. And we carefully studied how common textbook knowledge deals with moist processes. And all the books basically agree in this topic. There are different processes that lead to condensation in the air atmosphere, but by far, condensation by adiabatic expansion is the most important process by which atmosphere condenses water vapor. So we decided to study adiabatic expansions. Adiabatic expansions, we studied the ascending of an air parcel that is isolated from the environment. I mean, there is no transfer of energy and mass through the boundaries of the parcel. And it's something like the ascending of a balloon in the air. In an adiabatic expansion, the air parcel expands and cools, and then condensation happens. In an adiabatic expansion, then, changes in pressure, temperature, and condensation are not independent. So we work from common textbook knowledge, from all the equations of these books, and we reach to one equation that I want to show you. That is this equation. Here we have changes of pressure related with changes of temperature, and condensation is implicit, is inside this equation. What is very interesting of this equation is that we wrote this equation in a very special way. The first term is clearly the contribution from the derived fixes. That means that's adiabatic expansion without water vapor. And the second term is the contribution of condensation to changes in pressure. So we now separated the effects of condensation from the effects of the derived physics. What we can rewrite this equation in a more explicit way. Again, the first term corresponds to derived physics, and the second term corresponds to the condensation contribution. And this second term, it's really interesting. If we rewrite this equation in this form, we clearly show that this term, the condensation effect, has the form that the Russians proposed in their equation. So clearly, biotic pump and this evaporative force that the Russians proposed is inside the theory. The evaporative force can be explained from common textbook knowledge. So this brings us to the attention, okay, so the biotic pump theory is actually a theory of moist circulation. It's just moist convection. And the consequence is that the biotic pump hypothesis is implicit in what we know as moist convection. The biotic pump, therefore, is not doesn't add new physics to what we know of atmospheric dynamics, although it may offer a different point of view to study moist-related problems. The main idea I want to transmit in this talk or message is that since the publication of this work, there is an increasing interest to test this hypothesis. And the main efforts go in the direction to test this hypothesis by observations and by building models that introduce the biotic palm theory inside. If the effect of the biotic palm is in fact implicit in the classical picture, therefore, we can say that if we try to study and to find difference between using observations, we will find that observations will both agree with the classical and the biotic palm hypothesis. So we will not reach any conclusion from this way to solve this question. If we try to use models to test this hypothesis, if we look for a model that really has inside a real representation of condensation and water vapor processes, then we will have a model that will have inside the biotic pump. So now the problem will be, okay, which model have a real representation of convection and water vapor processes? That will be another problem, not related with the biotic pump, but related with choosing convection parametrization or cloud modeling models. So models will not offer a way to answer questions related with this hypothesis, because the biotic pump will be inside a model that really represents water vapor processes. So to finish this talk, I want to point the conclusions. The main conclusion, the main message I want to transmit here is that the controversy created by the biotic pump theory is calling our attention to the importance of how theoretical foundations, to strong theoretical foundations, to have a better understanding of the atmospheric processes and to clearly solve any kind of controversies that may appear. The evaporative force can be deduced from common textbook knowledge, and therefore it's always been inside the classical theory. The biotic pond hypothesis does not offer a new physics to study atmospheric dynamics, but it may offer a different point of view to study moist-related problems. And finally, efforts to test the biotic pond hypothesis must be made from the theoretical standpoint. Observations and models will not offer viable ways to test this hypothesis. So that's the main ideas. So thank you very much.
I hope I don't take too much of time. If anyone wants to ask a question, please come forward. I think I enjoy your talk very much, and I totally agree with you that this biotic pump, it's mainly emphasize the water vapor, its influence on the air density, therefore pressure gradient. And what is very helpful of this concept is bring the attention to the role of the vegetation and biosphere. And I really think your study really very beautifully illustrate this message. Like, it's important to consider this fact, but this fact is included in the fundamental dynamic equations, and I really appreciate that. And the other, if I may, I think I forgot to thank Sarah in my introduction, and I was really appreciate that she spent a lot of time with me despite of a very busy schedule. And it's also so happy to see that our Georgia Tech family member rise to the leadership position. Thank you.
Buenos días. Vos mencionabas que ambos enfoques son útiles para explicar muchos de los procesos atmosféricos, ¿cierto? De pronto existe alguna relación entre la bomba biótica y el enfoque termodinámico, o tal vez desde la termodinámica se pueda explicar la bomba biótica.
In English or Spanish? Okay. The question is about, I don't understand how to translate this in English. Well, okay, I will try. So you are asking if we can explain the biotic pump from thermodynamics or something like that? Okay, all the hypotheses of the biotic pump comes from thermodynamics. So hydrostatic balance, that is the key concept here, is just thermodynamics. From the theoretical perspective, what we found is that the theory, so the conclusions of the Russians, they had been rejected by reviewers because it's hard to understand what they are trying to explain, because they are explaining what we know in a very different and maybe a very strange way to say the same things. So we, from common textbook knowledge, so what we know about moist processes and from atmospheric thermodynamics, show that the key concept, this force that these Russians propose, are in fact inside, comes from the equations of thermodynamics. So it's so that I guess that answers the question. So we can explain the biotic pump theory from thermodynamics. That's the way to show how this theory might be right. One important message here is that most of the academic community rejected this work, the work of these Russians, saying that it was wrong, but nobody tried to show if it was really wrong. And the message here is that the Russians, although doesn't offer new physics, they are calling attention of what Professor Fu said, that is the importance of the operation and the importance of forests in atmospheric dynamics. Although we found that the biotic pump doesn't offer new physics, they are telling us that we need to study the role of the forests with the physics we know.